of two SHMs of one SHM. The equation of displacement is x1 is equal to a1 sine of omega t plus phi 1. A1 is its amplitude and phi 1 is its initial phase. And displacement of second SHM is x2 is equal to a2 sine of omega t plus phi 2, where a2 is its amplitude and phi 2 is its initial phase. When we combine these two SHMs together, the resulting displacement of a particle due to the combined two SHMs, x will be equal to x1 plus x2. So x is equal to a1 sine of omega t plus phi 1 plus a2 sine of omega t plus phi 2. Now, for this sine expression, we can use the formula sine of a plus b. And so here, the expansion can be sine of omega t cos of phi 1 plus cos of omega t sine of phi 1 plus a2 into, yes, this can be written as sine of omega t cos of phi 2 plus cos of omega t sine of phi 2. So this can be written as a1 sine of omega t cos of phi 1 plus a1 cos of omega t sine of phi 1 plus a2 sine of omega t cos of phi 2 plus a2 cos of omega t sine of phi 2. Now from this expression, sine of omega t and sine of omega t we can take common, and so this becomes equal to x is equal to sine of omega t into bracket a1 cos phi 1 plus a2 cos phi 2. From this expression, a1 cos omega t sine of phi 1 and a2 cos omega t sine of phi 2, we can take out cos of omega t common. So plus cos omega t into bracket a1 sine phi 1 plus a2 sine phi 2. Now in this expression, for this value, we'll take some substitution. Similarly, for this value, we will take one substitution. Let a cos delta, what substitution we have taken? A cos of delta be equal to a1 cos of phi 1 plus a2 cos of phi 2, and a sine of delta be equal to a1 sine of phi 1 plus a2 sine of phi 2. So by substituting these values in this particular expression, we'll get the expression of resultant displacement as sine of omega t into bracket a cos delta plus cos of omega t into a sine of delta Means this expression can be written as A sin omega t cos delta plus A cos omega t sin delta. So if we take A common into bracket, this will be sin omega t cos delta plus cos omega t sin delta. So this is the expansion of the term sin of omega t plus delta. Same formula again, sin of A plus B. And so over here we can write the equation of resultant displacement x as A sin of omega t plus delta. So in composition of two SHMs, x1 is equal to a1 sin of omega t plus phi 1 and x2 is equal to a2 sin of omega t plus phi 2. For these two SHMs, the composition of two SHMs which are executing on the same path about the same mean position, the resultant displacement is also following the same rule as that of the simple harmonic motion. This is the expression for displacement of simple harmonic motion, where A is the resultant of the two amplitudes. Omega t plus delta is the phase of SHM and delta is the resultant initial phase. And so the composition of two SHMs, the combined displacement is of simple harmonic motion. Now from this particular expression, let us try to find out a resultant amplitude A and a resultant initial phase delta. Now in order to find these two values, let us take our consideration again as A sin delta is A1 sin of phi 1 plus A2 sin of phi 2 and A cos delta is A1 cos of phi 1 plus A2 cos of phi 2. This is our consideration where we have taken the substitution as A sin delta and A cos delta. Now what we'll do is we'll square these terms. So squaring these two equations we get by squaring the expressions. This will be A square sin square delta. This will be equal to A1 sin of phi 1 plus A2 sin of phi 2 the whole square. And A square cos square delta, this will be A1 cos of phi 1 plus A2 cos of phi 2 the whole square. adding. This will be a square sine square delta plus a square cos square delta. This will be equal to a1 sine of phi plus a2 sine of phi 2 the whole square plus a1 cos of phi 1 plus a2 cos of phi 2 the whole square. So from this expression we will take a square common. So a square in the bracket sine square delta plus cos square delta. This will be. Now let us have an expansion of this first term. A plus b the whole square. This can be written as a1 square sine square phi 1 plus 2a1 a2 sine of phi 1 sine of phi 2 plus a2 square sine square phi 2 plus expand the second term a1 square cos square phi 1 plus twice a1 a2 cos of phi 1 cos of phi 2 plus a2 square cos square phi 2. Now in this expression we know sin square delta plus cos square delta is 1. The simple rule, sin square a plus cos square b, cos square a is equal to 1. Therefore, on the left hand side here it will be a square, this is equal to. Now in this addition, take a1 square common. So a1 square into bracket sin square phi 1 plus cos square phi 1 plus from this term take a2 square common. So a2 square will be sin square phi 2 plus cos square phi 2 plus from this term take twice a1 a2 common. So sin of phi 1 sin of phi 2 plus cos of phi 1 cos of phi 2. Therefore, a square is equal to a1 square into this term will be 1 plus a2 square sin square phi 2 plus cos square phi 2 will be 1 plus twice a1 a2. This is the expansion of, see, cos of a minus b is cos of a cos of b plus sin of a sin of b, and so this can be written as cos of phi 1 minus phi 2. See, if phi 1 is greater than phi 2, then cos of phi 1 minus phi 2 the angle will be positive. If phi 1 is smaller than phi 2, then phi 1 minus phi 2 will be angle will be negative, but cos of minus theta is cos of theta. So which angle is bigger is immaterial. And so over here a square become equal to a1 square plus a2 square plus twice a1 a2 cos of phi 1 minus phi 1. So from this we get the resultant amplitude as A is equal to under root A1 square plus A2 square plus twice A1 A2 cos of phi 1 minus phi 2. This is the expression for resultant amplitude in composition of two SHMs. Now in this case, suppose A1 is equal to A2. So let us take this as small a is equal to A1 is equal to A2. So both the displacement are having the same amplitudes. A1 is equal to A2 is equal to A. Then the resultant amplitude capital A will be root of A square plus twice A into cos of phi 1 minus phi 2. So this will be root of 2A square plus 2A square cos of phi 1 minus phi 2.